Hi everyone, good afternoon. Today, let me introduce our recent work to you, which is about semi-supervised context discovery for peer-based anomaly detection in multilayer networks. This is a joint work with my colleague, Micheal, Yusan, Yuzhong, Fei, Wanxin, Krupa, Yimin, Chinna, and Verma. And this work is conducted by Bo when she is an intern in Visa Research. The goal of this work is to detect intruder in a company-wide usage. So the idea is that we are trying to model the normal behavior of an employee or group of employees, and then if someone is coming but its behavior is very different from the employee groups that the person belongs to, we can announce that this person is an intruder. For example, we can use the number of internal websites visited per day as a metric. And you know that normal employees, they may visit like 2 or 3 internal websites, but if an intruder comes, the person may views like hundreds or thousands of websites every day. So we can using the standard deviations of this intruder in terms of the number of websites visited per day to detecting this person. So firstly, we need to model the peers' behavior by looking to how many websites the peers of the intruder they visited. And then we can use the standard deviation to compute the equation we're showing on the above, and then as using it as a metric to detect whether this person doing something normal or not. But we need to find the correct peers for this employee, right? For example, if the employee is a system admin, and if her or his job is to look into different websites and see whether there's some bug or not, so that person may not be a abnormal employee or intruder because their daily work is doing the website browsing. So now the problem becomes how we are able to detecting the correct peers for given employees. As you may know, the definition of peers is not that clear in a company. We can look into the HR table and look into the report chain of the person to decide what kind of peers. We can also look into the title of the person to decide the peers, but we can also look into the resource the person is using, if they are sharing the same service or not, and decide whether they have shared some property of their daily works, and we can use that to decide what kind of peers of the employee. So the peers have different definition. And in here, we show a more complex scenario, right? So different persons are linked by the resource they're using inside of a company. For example, in the first layer of the graph, we can look into email interaction, and we can also look into a big key interaction, how many wiki pages they're using, and also we can look into a server, as we already mentioned. So they are all the resources that can decide what kind of peers the person belongs to. And the person or the employee can be seen as a pillar that connecting the different layer of the graph. So here we propose multi-layer graph problem. And the unique contribution of this work is that we are trying to propose a way to weight the different layers of the graph so that the correct peers of the employee can be decided automatically based on the human feedbacks or the property of the graph. So we propose a framework that can using the semi-supervised machine learning and unsupervised machine learning to decide how we can weighting the different layer of the graph. In the supervised setting, we can using the human feedbacks to guide the weighting process. But in the unsupervised setting, we can use the clustering, and also later we can see the score alignment to finish this process. Here is the image we show in the paper. In the left, we're showing a simple usage, which is the node corresponding to the employee, and the servers are the resource they're using. You can see like different persons, they may have different server usage. In the right, we show the physical distance, right? The distance, whether the persons are connecting or whether the server is connecting or not, and how far they are beside each other. And in the most right, we see the active scores. They are the attributes we are trying to use to detecting the anomaly nodes. And here we show up 2 layers that is able to weighting the servers and the physical distance. So if we weighting all the nodes in the left way, we show in G1, we are able to using the peers of 1, 2, 3 to detecting whether the node 1 is anomaly or not. But if we weight in the right way, right? So all the nodes are connected with each other. And we need to use in the node 1, 2, 3, 4, 6 to decide whether number 1 is doing abnormal or not. So the 2, 3, 4, 6 becomes number 1's peers. And here are very different, right? And in this work, we are trying to find the optimal way to weighting this graph so that the final distance matrix can reflect the correct peer groups that can optimize or maximize our accuracy of anomaly detection. So that is the final goal of this paper. And here we propose the general frameworks, and this is a more detailed map. When we given different adjacent matrices or graph, we are trying to compute weights, right? But the weights is computed in a machine learning driven way. So we're using different loss functions to supervise this training process, and finally we can have an optimized way of assigning the weights to different adjacent metrics. So what we do is that we're using this weight to get a merged graph, and using the merged graph to find the peers for a specific node. And based on the attributes of the node, we can get an anomaly score. You can think this is a number of website visiting for employee, what we show in the first example. And the peers are decided by merging the multilayer graph. And finally, we can using the attributes of the peers and itself to decide the anomaly score. And finally, we can using the 3 loss functions to supervise the whole process. So what are the 3 loss functions? Here we're showing up. Firstly is the peer distance adjustment. We are trying to reduce the intra-cluster distance and keep nodes inside of the original peer groups. Second loss function, we are using a distance attribute alignment. We put nodes that have similar attribute values into the same cluster to reduce the potential fault alarms. And third, we use a list-wise learning to rank loss function. And it enforces few anomaly nodes rank higher than all the other nodes so that the information in the few labeled data can be largely utilized. And finally, we provide some experimental results. We conduct 3 experiments in this paper. First is a synthetic data, second is a sensor network data, and third is the cybersecurity data. In the first data, we have 6 layers and 500 nodes. In the second database, we have 2 layers and 54 nodes. In the third one, we have 3 layers and 1,926 nodes. Here is the result of the first experiment. What we do here is that we're trying to get optimal parameters for our loss function using synthetic data. What we're showing in the left is that if we're using this, you remember we have 6 layers, right? If we just use a peer grouping algorithm on each of the layer, and here is the AUC we got. And if we average out all the distance metrics, we got 0.47. And in the right, we're showing that when we using our algorithms, what is the final accuracy or AUC we can get. And here we set different parameters and trying to see whether the algorithm is robust or sensitive to each of the parameters. So we see that like if using the gamma equals 0.1 and then alpha and beta is assigned in the corresponding way, we can get optimal this kind of loss plan. So what is we used in the final experiment. And the second experiment is conducted on the sensor networks dataset. So in this dataset, we have 2 layers here. One is the communication strength, and second the geometric distance. So what we're trying to do is weighting these 2 layers so that each sensors may have optimal weight of peers, and we can use them to decide whether the sensor is run abnormally or is run in a normal way. So in the following table 4, we can see the experiment result. So ours actually outperform using a single layer, whether a coordinate layer or the communication layer, or using both of the layer, but averaging the distance to get the final peers. You can see our automatic peer selection is much better than their work. And in the right, we're showing a more graphic explanation. So what we're trying to do is we are trying to using our prediction to approximate the local ground truth-based peer grouping. So what we do is that we're showing all the anomaly cases here. The x-axis means time and the y-axis means which sensor is doing something wrong. So we can see like if you're using all the sensors as peers, you will get this kind of like a big, this kind of white region. But this part is something happened, we believe it's something happened in the environmental side. It does not caused by the individual sensor failure. So we are trying to look into whether there's some individual sensor failure here. So we are trying to approximate this kind of local ground truth. So we can think our prediction is very aligned with the local ground truth, which means that we are able to selecting the peers based on these two layers very well. So it can avoid that we using all the sensors as peer groups. So this experiment shows that our algorithms can select the peers more in a smart way. And finally, we show the results on the truly company-wide intrusion detection dataset. So here we have 3 layers. We name it Wiki access layer, second is the cloud application access layer, and third is the user server access layer. So we compare with the 3 state-of-the-art anomaly detection algorithms. You can see our results outperform 3 of the existing work. And we also compare with the peer grouping based anomaly detection systems, which using each individual layer, our algorithm also outperform them. We can also see that when we using all the layers to detecting the anomaly, our algorithm also outperform them. So in this work, we conclude that our algorithms is able to outperform all the existing works, especially the peer group based anomaly detection baselines, by a large margin. Finally, we come up with the conclusion. So in this work, we propose a multi-layer graph-based anomaly detection system where the anomaly is defined by considering the context and generated by combining individual layers. And the proposed system can be trained in both supervised and unsupervised fashion. And we also evaluate our system on both synthetic and real-world datasets. So our system is strong to capture the contextual anomalies in graphs and also outperform the compared methods. Thanks a lot.